Pluto, a distant and once considered planet in our solar system, has always fascinated astronomers and the general public alike. In recent years, discussions among leading astrophysicists, such as Neil deGrasse Tyson and Michio Kaku, have once again brought this icy world into the limelight. This time, through the provocative suggestion that Pluto could, in theory, be on a collision course with Neptune. This claim has sparked curiosity, speculation, and even concern among those who follow the mysteries of the cosmos. However, the central question that arises is whether such an event is truly within the realm of possibility, or whether it belongs more to the category of far-fetched cosmic hypotheses meant to remind us of the unpredictable nature of celestial mechanics. To begin understanding the matter, it is crucial to remember that Pluto, now classified as a dwarf planet, since its reclassification in 2006 by the International Astronomical Union, has always been remarkable not only because of its great distance from the Sun, but also because of the peculiar nature of its orbit, which differs greatly from the nearly circular paths traced by the 8 recognized planets. Instead, Pluto follows a highly elongated and inclined trajectory, taking approximately 2 for 8 Earth years to complete a single revolution around the Sun. Since its discovery in 1930 by Clyde Tombaugh, it has not yet even completed one full orbit, meaning that humanity's direct observational record of its motion is still relatively short compared to the scale of its journey through space. What makes Pluto's orbit particularly extraordinary is the fact that it crosses the orbital path of Neptune, a detail that immediately raises questions about whether such an intersection could ever lead to an actual collision. Yet despite this apparent crossing, Pluto has never collided with Neptune, and the explanation for this lies deep within the complexities of orbital mechanics and the subtle gravitational balances that maintain the harmony of our solar system. One of the most important reasons why Pluto and Neptune never come dangerously close is a phenomenon known as non-simultaneous vibration, which ensures that when Pluto's path brings it across Neptune's orbit, it is always positioned at least 90 away from the giant planet, meaning that the timing of their orbital positions prevents the two bodies from ever occupying the same place at the same time, a kind of cosmic choreography that protects both worlds from catastrophic impact. This spatial separation is vital because, without it, Pluto's eccentric trajectory would indeed pose a greater risk of instability. Adding to this protective mechanism is another concept in orbital mechanics known as orbital precession, which refers to the gradual shifting of the orientation of Pluto's orbit over long time scales. This shifting ensures that during its closest approaches to Neptune, Pluto is either well above or below the orbital plane of Neptune, meaning that even when their paths seem to overlap in 2 dimensions, in 3-dimensional space, they are significantly separated, further reducing any realistic chance of collision. Moreover, astrophysicists have introduced an additional stabilizing concept, sometimes described in terms of wobbling or oscillations influenced by gravitational interactions among Pluto, Neptune, and the Sun. This wobbling effect, examined by theorists such as Kaku and others, illustrates how, even though Pluto's orbit may appear erratic to the casual observer, in reality, the combined gravitational pulls of nearby massive bodies establish a long-term equilibrium that maintains its stability, preventing sudden chaotic deviations that could otherwise destabilize the system. Understanding such mechanisms requires grappling with the infamous 3-body problem in physics, which explores how 3 celestial objects interact gravitationally in ways that are often unpredictable and mathematically complex. In Pluto's case, not only Neptune and the Sun, but also the distant influences of the gas giants. Jupiter and Saturn play roles in subtly shaping its trajectory, acting almost as guardians that confine its movements within certain limits. One of the most elegant demonstrations of how Pluto and Neptune coexist without danger is found in their orbital resonance. For every 2 orbits that Pluto completes around the Sun, Neptune completes precisely 3, creating a 2-to-3 resonance that locks their motions into a predictable pattern, essentially serving as a cosmic safeguard against collision. This resonance has persisted for millions of years, ensuring that even though their orbits intersect, their actual paths remain choreographed in harmony. In addition to Neptune's influence, Jupiter's immense gravitational field exerts stabilizing effects that further help regulate Pluto's motion. Without the combined influence of Neptune, Jupiter, and Saturn, Pluto's journey through the solar system could indeed be far more erratic and perhaps even dangerous, however. Despite these strong stabilizing factors, Pluto's orbit is not immune to all irregularities. This is where the discussions by astrophysicists such as Tyson and Kaku gain significance. For mathematical simulations conducted in the 1980s revealed that even minor changes in Pluto's initial conditions could, over extremely long timescales, result in substantial deviations in its path, underscoring the principle that even stable systems are subject to eventual unpredictability. These simulations demonstrated that while Pluto's orbit is remarkably stable over millions or even billions of years, the accumulation of tiny perturbations, perhaps, from passing celestial objects or from subtle gravitational nudges within the solar system itself, could lead to more dramatic consequences in the far future, introducing an element of cosmic uncertainty that scientists must take seriously, even if the current risk is negligible. Tyson, who has long been vocal about Pluto's status as a dwarf planet, and who emphasizes the need for precision in our classification of celestial bodies, has pointed out that while Pluto's current resonance and gravitational interactions provide stability, the long-term trajectory of any body in space can never be guaranteed with absolute certainty, because orbital dynamics are inherently chaotic over sufficiently vast timescales. In his view, even a small shift, accumulated over millions of years, could one day lead to unpredictable outcomes, though certainly not within any time frame relevant to human existence. Michio Kaku, theoretical physicist known for exploring the broader implications of cosmic phenomena, has echoed this sentiment by stressing that planetary orbits, while seemingly fixed and orderly, are in reality maintained through delicate balances that are always susceptible to change. He has suggested that if a significant external force, such as the gravitational influence of a passing star or rogue planet, were to interact with our solar system, it could potentially alter Pluto's trajectory enough to disturb its current resonance with Neptune, an event that could indeed sow chaos into the carefully orchestrated motions of the outer solar system. Both Kaku and Tyson make it clear, however, that the probability of an actual Pluto-Neptune collision occurring in the near or even distant future remains extremely low. Yet they argue the continued observation, study, and modeling of these orbital patterns are vital not only for understanding Pluto itself, but also for gaining a clearer picture of the long-term evolution and stability of our solar system. Pluto's case serves as a fascinating microcosm of how celestial bodies, despite appearing chaotic, can maintain stability through subtle resonances and gravitational dances. It highlights the broader scientific concept of orbital chaos, which suggests that even tiny differences in initial conditions can, over immense stretches of time, lead to vastly different outcomes. Modern computational models, equipped with advanced simulations, have allowed astronomers to explore Pluto's motion across many potential scenarios, testing how its orbit might evolve under different conditions. While these models confirm the overall stability of Pluto's unusual trajectory, they also remind us of the inherent limitations of prediction. For even the most sophisticated mathematical frameworks rely on precise inputs, and any slight error in these initial conditions can amplify into dramatically different long-term forecasts. This limitation of prediction underscores the humility required when studying celestial mechanics, reminding us that the cosmos is dynamic, ever-changing, and full of surprises. While we can make confident statements about stability on certain scales, absolute certainty always remains out of reach. Pluto's orbit, with its elongated path, inclined plane, and resonance with Neptune, exemplifies the intricate balance that governs planetary motion within our solar system. Despite its eccentric nature, the gravitational influences of Neptune, Jupiter, and Saturn act as cosmic guardians that keep it in check, preserving stability for the foreseeable future. At the same time, the discussions raised by Tyson and Kaku serve to emphasize that, even in such apparently stable systems, the possibility of change always exists, whether through gradual perturbations that accumulate over billions of years or through sudden external influences that we cannot yet anticipate. This recognition is why astronomers stress the importance of continued study, monitoring, and refinement of our models. The story of Pluto is more than just about one dwarf planet. It is a reminder of how fragile and delicate the harmony of the solar system truly is, how minor shifts can lead to dramatic consequences, and how much remains unknown despite centuries of astronomical progress. As new telescopes, such as the James Webb Space Telescope, and future planned observatories continue to provide unprecedented data about the outer reaches of the solar system, our understanding of Pluto and its interactions with other planets will only deepen, revealing perhaps even more mysteries about this icy world that once held the title of ninth planet but now occupies a more enigmatic role as a symbol of the complexities of celestial classification and orbital dynamics. The fascination with Pluto, whether it concerns its unique orbit, its icy surface, its possible subsurface ocean, or its symbolic status in the cultural imagination, continues to captivate scientists and the public alike. The debate over its potential collision with Neptune, though highly improbable, illustrates the broader theme that the universe is never static but constantly evolving, a place where even systems that seem stable today could undergo profound transformations over cosmic timescales. In the end, whether or not Pluto ever veers from its current path to create a cataclysmic encounter with Neptune, the study of its orbit provides an invaluable opportunity to refine our knowledge of orbital mechanics, to appreciate the delicate gravitational choreography that underpins the solar system, and to remain vigilant to the possibility that new discoveries may yet reshape our understanding of planetary dynamics in ways we cannot now predict. Thus, Pluto's journey is not merely a story about a small, icy world at the edge of the solar system, but a window into the very forces that structure our cosmic neighborhood. As we look further into the future, with ever more advanced tools, we may uncover revelations that alter how we view not only Pluto and Neptune, but also the fundamental stability of the solar system itself, reminding us that the quest for knowledge is ongoing and that the mysteries of the universe remain as vast and compelling as ever. Furthermore, when we consider the broader implications of Pluto's orbital dynamics, we are reminded that the solar system itself is not a perfectly ordered machine, but a dynamic environment shaped by constant motion, gravitational pulls, and occasional disruptions. While modern astronomy has given us the ability to calculate orbital paths with extraordinary accuracy, the truth is that over billions of years, interplay of forces can introduce a degree of chaos that no equation can fully tame. If we entertain, even hypothetically, the idea of Pluto eventually breaking free from its protective resonance with Neptune, the consequences could extend far beyond these two celestial bodies. For the disruption of one orbit has the potential to send ripples throughout the system, subtly altering the paths of other objects.